Okay, so we actually know some other stuff. So we use this kind of logic all the time. This is sort of the basis of all of human intelligence, like I said. So, for example, we know some stuff in regular math. Like, if x is less than y and y is less than z, what do you know? X is less than z. Does anybody know what that's called? Transitive. Okay. Now, what if I put a less than or equal to on there? It's still less than or equal to, right? So less than and less than or equal to are all transitive. So that means if I know two relationships and the conclusion of one is the same as the hypothesis of the other, it's going to be there. So actually less than or equal to is the same as implication. So P implies Q. Another way you can remember it is the same in logic as P is less than or equal to Q. So what that's saying is Q is true at least as often as P is. Okay, so we can do, from this same math rule, if these are the same, then we actually should be able to do transitive with implication, right? So if I know P implies Q, and we know that Q implies R, what can I get? P implies R. Now, if I know P implies R, can I get these other two? No, so another way I like to think about this is flights, because these kind of look like diagrams for flights, right? So if I can fly from Paris to Quebec and Quebec to Raleigh, that means I can fly from Paris to Raleigh, right? But just because I can fly from Paris to Raleigh doesn't mean necessarily that I can go through Quebec to do it, right? So this implication only goes from left to right. So when I'm going from left to right, I'm losing information, right? I'm learning a new fact, but it's not telling me as much stuff about individual things in the world. So I'm going to try to give you lots of analogies for each thing that we do and have them make sense to you. Connect it to something that already makes sense to you. So most of the math we're doing in here, you've actually already done it in some form or another, just with some regular numbers, not binary numbers. Okay, this is called, it should be called transitive, but it has another name, which is hypothetical syllogism. Now, I'm okay with being lazy, so you can write HS. But you should still know what we're talking about when we say the words out. Hypothetical syllogism. Okay, so we can prove this with a truth table. Does anybody want to? No, it's easy. Truth tables are easy, right? You just fill them out. Like whatever values you can, you fill them out. And then you just look for ones in columns that have these double arrows. That's it. They're easy to do. Okay? All right, so why are we doing all this mess? We're doing all this mess because we want to do formal proofs. So formal proofs are where we actually can logic through, reason through some things, and derive new things. So these are proofs that use the axioms to derive a conclusion from a hypothesis. Is this related to any operation that we have talked about today? It's related to implication. So when we prove things, we're actually proving an implication. So what we usually have is something like this. H implies C, where H is my hypothesis and C is my conclusion. And I have a double bar here, which means that as long as I know H is true, then C has to be true. So as long as the hypothesis is true, the conclusion has to be true. But we have to prove it somehow. So it is our job. So this is a really core computer science idea, is that whenever it's your job to prove something, you should think of having an adversary that's going to try to poke holes in whatever you do. And truth tables are one thing you can't poke holes in. As long as you've filled out all the values, like there's no magic that's going to happen and flip one of the values in there. Okay? So that's like a table. Here's all the, this is a table of everything that could happen with P and Q and all the outputs. There's no arguing with it. You can't argue it. Same thing, you want to do a formal proof in that way. There's no arguing with it. Why would we want that as computer scientists? What'd you say? We want to test all cases. Okay, what else? I want to make sure people can't break my programs. I do. How many of you people are not worried about your programs getting broken? Okay, you're not worried. Okay? How many of you know that airplanes are flown by computers? How many of you would like them to break? Like them to break. You don't fly, do you? Okay. When we're writing super important code, we have to prove that it's going to do what we say. So proofs is an integral part of doing computer science. You may not do it all the time, but you have to know how to do it, and you have to know how important it is, because human lives depend on these things working the way we say they do. So we often have to, when we have super important programs that have responsibility for people, we have to make sure they work the way they're supposed to. And so one way we do that is by proving that they do what we say. How do we do that? Well, we're going to do basic, easy proofs now. We're not going to do super hard proofs about like how complex code does what it does. You can take a whole class on that. So we're not going to do it. But that's the reason why we do this kind of stuff. And it's also because this is the core, like I said, of when we build software that tries to simulate how people reason. This is the core idea of it. So that software uses if-then rules all the time. Okay, so what do? I might give you something like A implies B, and B implies C, and A as some givens. So I might write a problem like this, and I might say prove C. So these three things are given, and I'm going to prove C. Now, in a proof, if things are given, we assume a little and in between all of them. So A implies B is true, and B implies C is true, and A is true. So by writing it, simply writing it, I'm claiming that it's true. Now, I'm not claiming this is true, so it's kind of like I have a little question mark over it. So I want to show that C is true, but I don't know yet. So when I'm given a problem like this, then I'm going to write it down in what's called a formal proof. So I'm going to copy over the givens, and I'm going to put numbers next to them, and I'm going to write down that they're given. And up at the top, I'm going to write what I'm trying to prove because I don't want to forget. So we always have numbers, we always have statements, we always have a reason, and this is just a note, but we do have it at the top just to remember what we're doing. Now, doing proofs is not always intuitive, but there's some easy stuff we can do. We can do some pattern matching. What I like to do is look at what I'm trying to prove and find it in my proof. I see it on line 2, right? But line 2 has some other mess on there. I don't want it. I need to get rid of it. So I need to find a rule that actually helps me get rid of it. Well, we actually just talked about one, right? So I can get rid of this B if I had another implication that implied B. Oh, I do. So I've got A implies B and B implies C, so I can get A implies C from 1 and 2 and hypothetical syllogism. Any questions about that? So that's great. I got rid of the B. Oh, no. I still have an A there. Would like to get rid of that. Okay? Well, handily enough, we have an A on line 3. If I combine it with line 4, what do I get? I get C because if I have A implies C, that's like if it's raining, I'm getting wet. And line 3 says it's raining, so therefore I must be getting wet. That is modus ponens. So another thing we're doing here is every time we use a line from my proof, we're giving it a number in the reason, and then we're saying what rule we used, what axiom that's on your list that we used to derive that. So we wrote out modus ponens differently on a line before, yes. Yes, it's a handout on your Moodle, and when you have a test, we will give it to you. However, you're going to be using them a lot, so you probably won't need it, but it'll be good just to be able to look at it. So you are allowed that. We give it to you during the test. You don't even have to bring it. Okay? So I don't recommend, while you're doing proofs, to just look at your list of stuff that you're trying to prove. Like, you know, when I'm sitting here with this, don't look at the list. I think you should make a wish. So I have a double math major as undergrad and as a grad student. So in master's, I have a master's in math and undergrad in math, and also in computer science. And the reason why I'm mentioning that is that learning proofs was torturous. And it's torturous for everybody. So don't think that when you're doing like this was the easy one, you're going to do some harder ones, okay? You're going to do quite a lot of harder ones. And you're going to be like, oh my goodness, what do I do? What you do is you make a wish for what you would like, and then you see if you can make that happen. So that's what I did. So I looked for what I was trying to prove. I was like, I'm going to wish that C is somewhere in this list of givens. Because if it was already there, I wouldn't have to do anything, right? Okay, well, I found the closest I could. And then I made a wish that this B would go away. And then I looked for a place where I might be able to make B go away. The only way I really can get it to go away is by finding its opposite and canceling it out, basically. Right? And that's what we did when we did our transitive rule. Like when x is less than y is less than z, we kind of get rid of that y when we go to x is less than z. We're doing the same thing with hypothetical syllogism. We're getting rid of a variable. That's what we wanted. So we make a wish, and then we try to fulfill that wish with the rules that we have. And we do this with writing programs too, don't we? Right? Like we make a wish. I wish I had a function that would print out all the values in this list. Oh, yay, there's already one in here, or oh, no, there isn't. I have to write it. Okay? So we do this all the time. You already do it. You just might not have done it for logic. But you're doing it for writing programs. And this is really good practice for this. So we're going to do some other problems like this. We talked about, so the rules we talked about today were implication rule, although I didn't actually necessarily write it that way. So what that means is whenever I see P implies Q, I can replace it with not P or Q. We did modus ponens, which was P, ended with P implies Q, logically implies Q. We did hypothetical syllogism. By the way, the word syllogism just means like truism. It means something that's true. So it's the thing that's true about statements with hypotheses. Okay? So that's if you have P implies Q and Q implies R, then that gives you P implies R. This is probably going to be your favorite. And it shouldn't be your favorite. Okay? Disjunctive syllogism says if I have not P or Q, actually, it says if I have P or Q, it doesn't have a not on there, sorry. It says if I have P or Q and I have not P, then what do I get? So if I tell you I have an apple or an orange, and then I say I don't have an orange, I must have an apple. So if I have an or, and I know one of the parts of the or is false, then the other part has to be true because or preserves truths, right? So there has to be a true in the source. So we must know that Q is true. So this is called disjunctive syllogism. The reason why I say it shouldn't be your favorite is because it's not as useful as the ones that have implications in them. Because we're also sometimes going to have to use the hairy and yucky distributive rule if you insist on using disjunctive syllogism. So I'm going to write it down and then we're going to stop. So distributive rule there's two of them. Okay, now, I really don't like this one. I don't like it because it's so easy to mix it all up. Now, the way to remember it, though, is that it works exactly the same way as regular math for one of the cases, where we think of or as plus and we think of and as times. So which ones of these works like you would expect? Anybody look at that and figure it out? Okay, so if we translate this into math, that would be, the first one would be PQ plus R equals P plus R times Q plus R. That doesn't look right to me. That's not regular math, because you have to use first, inner, outer, last. You're going to get R squared in there, right? This is not regular math. The second one, let's write that. P plus Q times R is logically equivalent to PR plus QR. Hey, that works like I expect it to. So distributive, when you have the and on the outside, works just like your regular math. And it works the same way for and or. It's because we don't have order of operation in logic, but we do in regular math. So times always comes first in regular math, which is why this is false. Okay, but in logic, whatever the parentheses say is what you do. All right, so just to remember, help you remember it, you take the first, if I'm going to distribute an operator across a parentheses, you always, what you distribute ends up across, so the and R is going to be everywhere, and you just take the other ones. So you take the first variable and put it with and R, you take the second variable and put it with and R, and put that operator in the middle. See you next time.